Lean is a programming language as well as an interactive theorem prover. And so there's a lot of interest in it to make, for example, AI output safe. Right now, I'm going to just give a quick introduction to how Lean looks, how it resembles and is different from other programming languages. And I'm working on the Lean playground. So with zero installation, you can go to live.leanlang.org and try what I'm doing now. Okay, so let's define the smallest element in a list and a list of integers. So simple enough program, but it'll already illustrate some nice features of Lean. Well, one of the things we can do in Lean is use pattern matching. In fact, that's the best way to do this. So what are the different patterns? If I have a list with one element, then of course the smallest element is that element. What if I have a list with two or more elements? The way we'll write that in Lean is with the first element is x, and colon colon means we prepend it to y is the second element and to all the rest. Okay, so y and z is the tail. This pattern ensures it's non-empty. Well, in this case, what is the value? It's the minimum of the first element and the smallest of the rest. Okay. One thing to get used to is functional languages can allow omitting of parentheses. So I didn't need parentheses around x, but I do need them to say y and z's are together. Okay, that looks great, except that we have, as we see, a red line here, and we click on this, we will see in what is called the info view that we missed a case. What the case we missed was an empty list, and Lean gives a compile error. That's great. It prevents runtime problems. But what should we do in that case? There is no smallest element. Well, right now what I'll do is something which is fine in this kind of case, which is give us a junk value, but in other cases can be dangerous. So I put a comment that this is a junk value. And so we'll have to learn how to avoid giving things like junk values. That's in safety critical things, and not just safety critical things, to make programming much easier and more pleasant. Now, in some languages, you can have a type of non-empty lists and say we were going to define only the smallest element of a non-empty list. But in Lean, you can do better than that. You can define an arbitrary property. Okay. So to make space, I mean, in my names, I'm going to rename the smallest sub-zero. Another attractive feature of Lean is that you can give a much greater range of names. And smallest will be reserved for the way I want to do it, which is I'm going to take a list of integers. And then I'm going to take a property. And the property is that the list is not empty. Okay, I can write it's not equal to, it's in a mood to autocomplete, NEQ. It's not equal to the empty list. Okay, so I'm given a list and it's given that it's not empty to the equal to the empty list. And then I match L with. Okay, so let's see what we have. The first case is X. Again, it's X. And the second case is X, Y, and Z's. In this case, again, we want to take the minimum of X and the smallest of X and Y, the smallest of this list, Y colon colon Z. Well, we are not quite done here. The key point is that there was we have to prove that this list is not empty. Only then we can call smallest on it. Okay, so you'll see that slightly more obscure error. If I put an underscore, you'll see the error is more clearly. You want to show that this list is non-empty. Fortunately, Lean has these things called tactics, which make it easy to show them. By simplification, and we are done. So now you notice there's nothing right here. So we have really gained something. We avoided the missed case, and we could show things are legal. But there are all sorts of other logical errors we could make, and this is where the power of Lean really comes in. Okay, so what do we need about the smallest element? First of all, the smallest element has to be an element of the list. So we can prove that as a theorem. Conventionally, this would be called smallest mem. Mem is a member. Okay, so let the hypothesis is similar. First of all, we have a list of integers. Okay, and we have h, which is going to be that the list is not 0. And here, instead of returning an integer, we'll return a proof. And what is the proof? That the smallest element of the list and we have to be given the hypothesis for this function to make sense, is an element in the list. Okay, and so we can prove this by getting into tactic mode. Okay, so what we want to show, you'll see on the right hand side on top that we have to prove the smallest is in this. Okay, this could be hard work, but fortunately Lean has a lot of nice automation. And in particular, there's fun induction because this is a recursively defined function smallest. So I can do functional induction on it. Okay, it's also fun. So good name, small induction. And then we have a bunch of cases to prove. Well, we have to work a little in the cases, except that we have a tactic called grind, which just does it. So great, we have proved that the smallest member is an element, the function value returned by the smallest function is actually an element in the list. Well, there's one more thing we have to prove. That is that every element in the list is greater than or equal to the smallest element. Okay, or the smallest element is the least element in the list. So I'm going to call this smallest LE. That's the conventional name. I'll just copy paste the proof and the statement. Of course, the statement is wrong here. The real statement we want here is that if I take any element in the list, so if I take for all x in L, and I don't want smallest L, h is less than or equal to this. What I want is LEQ x. And you see, when we, remarkably enough, the same proof work, because fundamentally the pattern is the same. Okay, that is to say, we have the smallest element in the list is we induct on smallest, we get a nice induction hypothesis and everything like that, and the tactic grind does this for you. So this gave an example of defining things in Lean, which could be done in a naive way, but you could do it in a better way to make sure you don't have errors. And then to prove things, tell you that the definition is actually logically correct.